initial state, but we will study only the largest contribution and also at leading order. So for the production of either charged Higgs or neutral Higgs, the Feynman diagrams are only for these three with E plus E minus to H and with two fermions. Similar studies have been performed several 10 years ago in the 2 Higgs doublet model, but it's mainly on type 2. And in this paper, they studied only the production of these channels, and in this paper, they studied the production and similar symbol decays and also detector simulations, but it's necessary to make an update, and we also emphasize on the type 2 2-freedom model. So what we want to do is to make a thorough study on Higgs production with all types of Yukawa couplings at leading order.
Excuse me, in your LHC discussion, did you really cover the charge Higgs production?
ILC.
No, you were covering a lot of time about the reach for
yes.
for say high velocity LHC. Not just the charge Higgs, but what about associated production with single top?
HT.
Was that covered?
No.
So my question is just saying, what is the reach with single top? Because you want to...
You mean at LHC?
At LHC, yeah.
LHC.
No, at LHC, because I think you talked about, I think the previous slide you were showing all these limits, right?
The main channel will be from boson fusion to...
So these are all the neutral Higgs?
Yes, it's from
H and A.
Yes.
So that's why my question started with the charge Higgs. But also, the processes you talked about did not mention, single top associated production. Say TH, TA, and TH plus. I have no knowledge of it. My question is for you.
No, they have for the 2 Higgs model, and they have only studied the neutral Higgs to get the LHC constraints in this way, and no.
So anyway, you have not included a single top associated
and
production.
also no single top, yes.
Yeah. Right. So the question. Okay. So if you come back down. I guess I'll let you go and continue, but because the lower, in your first box, the TBH is like a single top associated production.
Yes.
So my question is therefore, what is the reach at LHC with very high luminosity for that type of modes, if it's not yet covered?
TH production.
Okay, I'm happy with the answer. We can come back to this for discussion.
Yes, I have some studied on that, but not included in this slide. And they have some constraints from the experimental part on TH associated production at LHC.
It actually is different because here everything is in the final state, but for single top you can utilize advantages. Okay, anyway, we'll go on and we can discuss it later.
Then after Higgs production, we consider how Higgs decays. The decay branch ratios of different decay modes can be partial decay weights can be easily calculated for neutral Higgs decays to QQ bar, neutral Higgs decays to leptons, and charged Higgs decays to up and down type quarks, and also charged Higgs decay to leptons. The corresponding functions are different for CP even and CP out neutral Higgs, and also it is defined here. For the we also include Higgs to glucose, and we can also get easily the partial decay weights of neutral Higgs to glucose with corresponding fermionic loop functions given in this way, and here C0 with the PV functions, and also the corresponding F functions are defined here. Then for we know that charge Higgs decay will be different if when charge Higgs mass below or above the top quark mass. So we choose value at Higgs mass to be 150 GeV as an example of Higgs mass below top quark mass. So for the different types of type 1, 2, XY, the branching ratios are different in this case. This is for the CP even neutral Higgs. In the type 1, it doesn't change with the tangent beta, and the largest decay mode is always BB, H2BB. And in the tangent beta, in the type 2 case, in smaller tangent beta, it is glow. In tangent beta larger than 1, it is also BB dominated. And it's a similar case in type Y. And for the type X, in small tangent beta region, it will be BB. And in large tangent beta greater than 1, it's larger than the dominant decay mode is tau. This is for the CP even neutral Higgs. And for the CP odd neutral Higgs, it is slightly different. For type 1, 2, XY. Also for type 1, the largest is BB, and it doesn't change with tangent beta. And for the type 2 and type Y, the smaller tangent beta region decay is mainly to glow, larger is to BB. And similarly, the small tangent beta region Higgs, CP odd Higgs will decay to BB, and larger with tau. Also, the charge Higgs with mass 150 GeV, type 1 case, the largest branch, type 1, 2, X, the largest is tau nu, and also for the type Y case, the smaller tangent beta region is tau nu dominant. In the larger tangent beta region, it is CB dominant. Well, as an example of charge Higgs mass greater than top quark, then the Higgs will decay to top. So for we take Higgs mass to be 500 GeV, for example, and the first 4 figures are for neutral Higgs decay to neutral CP even neutral Higgs decay. The largest decay mode is TT bar in type 1, and in smaller tangent beta region, it's also TT bar dominant for all other types. And in larger tangent beta region, it will be BB and BB bar dominant in type 2 and type Y. Or in type X, it's larger tangent beta region, it is tau dominant. Or similarly for the neutral Higgs CP odd case, the decay mode of neutral Higgs is similar to the CP even case. While for charge Higgs, it will be the dominant region related to top will be charge Higgs to TB. This is the case for type 1, type 2, and type Y. And but for the type X, it is tau nu dominant in larger tangent beta region. Okay, then let's see our preliminary results. After we get the production and the decay, we can calculate the cross-section easily for the above mentioned processes. And for all different types, here is for as an example of ILC center of mass energy 500 GeV. These are counterplot of 0.1 femtobar. For counterplot, these curves are for these corresponding processes at cross-section 0.1 femtobar. And in the left part is the cross-section greater than 0.1. So this is type 1 and the type X case for neutral Higgs. In the lower 2 figures is type 2 and type X for the charge Higgs case at 500 GeV. And we can see that the different processes behave differently in this different type of Yukawas. Then let's see the result of counterplot for 0.1 femtobar at 1 TeV at ILC case. We can see that at 1 TeV the final state will be more interesting with 4 top channel opened, and we can see that for neutral Higgs in the larger Higgs mass and small 10 beta region, 4T can serve as a discovery channel. For the chat Higgs part, the TB channel also opened, and for the region with small 10 beta and large Higgs mass, we can see that it is also very special in this region.
Excuse me, I think my earlier question about, you plot all the way down to tangent beta of 0.1.
Yes.
Wouldn't the top quark Yukawa plane start to violate unitarity before that? Because the top mass is coming from a very small VU. Okay, so lambda T is therefore scaled up, and therefore TD bar scattering would violate unitarity, I think. It's a theoretical question, but just saying it seems not considered.
Okay, I will think about that. I don't know that if it is.
Because it's actually probably not uninteresting, because TT bar scattering, I don't know, to some exotic Higgs is probably enhanced. So once you look at, I don't know, high mass TD bar pair, high mass thing but created by TD bar system. Okay, just a comment why I was asking for really small tangent beta. Tangent beta above 1 would not have this problem. Even 0.2, 0.5 maybe not a problem, but 0.1, you have some strong coupling somewhere. Okay.
I think in 2 Higgs doublet model type 2, it should be, in 2 Higgs doublet model type 2, tangent beta should be bigger than 0.4 to not for the unitarity.
Yes, there's lower bound.
Yeah. So that's why I said in this plot they plot to 0.1.
Actually, here, most constraints is for type 2. Actually, for consistency, we studied tangent beta to be a very low region. It's mainly for type 1 XY. That is necessary. So for consistency, we also studied tangent beta at such low value for type 2. Okay, this is the all results that for different type of Yukawas at ILC 250 GeV in the first line, at for type 1, type 2, type X, type Y, and for the second line it is at ILC 500 GeV, and it is also for type 1 to XY. The last figures are for Higgs ILC 1 TeV case. You can see clearly that it is very sensitive to different types, the behaviors of chat Higgs production and decays at ILC. Also, this is only for the neutral Higgs final state. For the chat Higgs, we have similar figures, and at the 500 GeV and 1 TeV case I have showed you before. So this is also very sensitive to the different types of Yukawas, and as I mentioned before, at the 500 GeV and 1 TeV case, TB is very special is very interesting in the large chat Higgs mass region. We also that is calculation now for the signal without any cuts. And we also considered similar standard model background from the similar from the signatures that same as the signal at 200 GeV ILC, 500 GeV, and also 1 TeV ILC. These are the values we have now before any kinematic cuts. Because this is still a work in progress, so we will make further studies on this. Maybe by imposing the possible cuts to suppress the backgrounds and find a way to enhance the signal over background ratio. So that is our next steps that we want to do to make more realistic detector simulations and see the situations of the 0.1 contour plot after the detector simulation study. Then finally, I will summarize my talk. We made a complementary study on Higgs bosons in all types of 2 Higgs doublet models at ILC, and emphasize the parameter region beyond the LHC reach. Extra Higgs boson production and decay final states provides very distinctive signatures from different types of required interactions within the 2 Higgs doublet model. Then the single Higgs production above mass threshold is included and shows distinct signatures as discovery channel. Okay, thanks.
Questions? Okay.
Why didn't you include the 2 Higgs doublet model type 3 when you allow
type 3 is the type 3, type 4 is for the type 1, type X.
No, type 3 maybe the notation is different than what you use. That you allow both Higgs to cover to allow one Higgs to cover to both up type quark and down type quark.
Yes, that is our type 1.
No. He's saying remove the Z2 symmetry. Allow FC and Higgs.
Similar to that model.
Well, they explicitly did not consider it, that's clear. Type X and Y is just including the lepton sector. But you did mention in this context the Barbar beta D tau nu beta D star tau nu. So you just mention it and ignore it.
Yes.
Yeah, see, that's your answer. But this is also how we were discussing during lunch, that although the study is fine, but in terms of the 2 Higgs doublet model, the question is whether that Z2 symmetry is overly strong or not. Okay. It's a theoretical statement more than 35 years. Now we have finally reached it, and with the Barbar hint, should we be more open? Okay. So that's a useful reminder. Any other questions? Anyway, in your summary, the last line, the single Higgs production for the IOC gives unique signatures. That was my question, saying it seems not sufficiently covered in your LHC background discussion.
Yes.
That the single Higgs probably is in association with the top, or maybe a bottom at least, depending on tangent beta value. That looks like something we can still learn that you did not cover. Okay.
Yes.
Okay, so do that.
Your first statement, you said all types of 2 Higgs doublet models?
Huh?
All
You said
types.
all types. What about the inert 2 Higgs doublet?
What?
The inert Higgs doublet.
Inert.
Inert.
Okay.
This all types is the type 1 to XY as I introduced in the first task.
You tell us. Inert is for cosmology, right?
Yeah, it has that matter, but
Okay, I should replace this
So you want
word.
to give a talk next semester? No, it's interesting, but You think inert can really be studied in a collider?
Yes, Ari.
Huh?
Anders
Sorry.
Ari
Oh, okay.
did that.
Should have asked him while he was here. Huh?
He did talk about it, but you
Oh, he
are
did.
away.
I
You
was
are
not
away.
here. Okay. So what was the conclusion there for the inert?
Well, there's some parameter space.
As usual. Okay. Okay. Any other questions? I think for several questions, I think Ya-Juan also introduced it, but let me emphasize, we've seen at Higgs, are there others? What do they look like? How do we find them? It's an extremely important issue. It's not like in the past, I have background in 2x double models, but it was always a little bit fictitious. It's always indirect effects. Now it's a different thing, both for LHC and for the ILC discussion. So if there are no other questions with that impression, let's thank Ya-Juan again.